Following Copernicus's work, we move on to the next two big names in astronomy, Tycho Brahe and Johannes Kepler. I'll talk about Brahe first. Tycho was a very wealthy man, and he spent a lot of his fortune on creating the best astronomical tools. He actually employed dozens of people throughout his life to sit in an observatory and record the positions of stars and planets. And Tycho's great accomplishment was having this huge catalog of all the positions, a huge data bank. Johannes Kepler was one of these many people in Tycho's employment. And Johannes was a heliocentrist. Tycho was more convinced of a geocentric model, and they would go back and forth. They had a working, sometimes antagonistic relationship, both of them being very educated, smart people, but also disagreeing on what the data says. Kepler convinced that he could measure the wobble of the planets and use that to confirm that the Earth is orbiting around the sun. And Tycho, looking at his data, was convinced, no, it's not there. So after some history plays out, eventually Tycho passes away and Johannes inherits all of Tycho's work, or at least the bulk of it. And Johannes Kepler goes on to do what would be called an empirical science. Or modern days, you might call it data science. Johannes Kepler took a large data set and started processing it and pulling out rules. He doesn't understand why these rules exist. He doesn't have an explanation of why they happen, but he can, based on the data that Tycho collected over his lifespan, Kepler could predict and understand what those planets were doing. So with that, let's move into Kepler's three laws. The first of Kepler's law states that the planets orbit in ellipses. No longer are our perfect circles to fit a perfect universe. Kepler looked at the data and said, no matter how we try and measure this, the planets are orbiting in ellipses. So if you want to draw an ellipse, here's a picture of that. You could create two foci, two focuses, right? Draw a string around that, and then use your pencil to trace out the ellipse. If you bring the focuses closer, if you have focus here, if you have a focus here and here, you're going to trace out a more circular shape, right? So depending on the distances between the foci, and now we made a nice little sad face, but the distances between the foci determines how eccentric your ellipse is going to be. So continuing the statement of Kepler's first law, the planets orbit on ellipses. Ellipses have two focuses. The sun lives at one of the focuses. Nothing out here, nothing at the second focus. All right. So we can describe the ellipses with a semi-major axis and a semi-minor axis. The eccentricity, how stretched out, how crushed of a circle is this, is determined by factors of relationships on the semi-major and semi-minor axes, which we'll label as A and B. Kepler's second law is known as the law of equal areas. And what this means is that as the planet orbits the sun, so here's the sun at one of the focuses of the ellipse, here's the second focus. As the planet sweeps out, if I wait an equal amount of time, this much area, the pink here, will be the area shaded, filled in. And so let's say I wait another month. Where is the planet at this point? And it's moved. Well, here's a time span of 1 month. The planet has moved in 1 month in this picture here. Here's the amount of area shaded in pink. I'll do another one. And another. And another. And another. Right? So the amount of area filled up is the same. Here, we can put this all together in a nice little animated image and watch that go. So you see how no matter where the planet is, the size of this pink shade will change such that the area is always conserved. This area is always a constant. So this is what I mean by the law of equal areas. I wait, and each one of these pictures is about a month of Earth's orbit. So each month, this much area is swept out. And some things to point out about this. Notice how it gets close to the sun. Look how fast it's moving when it's close. Now look at how fast it's moving when it's far away from the sun. Look on the far edge. There it is. Notice how it slows down. So, when you are close to the sun, when you're closest to the sun, or in this picture I've flipped things around. When you're close, you have to move quickly. When you're far away, you have to go slowly. So in each one of these pictures, T1 to T2, T3 to T4, T5 to T6, you could say these are all 1 month. 1 month has passed for the planet while it's orbiting the sun. And each one of these shaded regions, shade A, B, and C, they're all the same area. Finally, Kepler's third law relates the square of the period to the cube of the semi-major axis. In essence, the time it takes for the planet to open, explicitly the sidereal period, right? The time it takes for the planet to orbit the sun is related to the semi-major axis, sometimes shorthand referred to as the radius. So the shortcut we'll say is that the square period is proportional to the cube radius. Now, to be semantic, to be accurate, we should say that the square sidereal period is proportional to the cube semi-major axis. But we shortcut to this because it turns out while the planets do orbit in ellipses, they are approximately circles. They're close to circles. So when we're lazy, we're being fast, we'll say the square period is proportional to the cube radius. And the consequences of this, it just means that the further away a planet is, the more time they need to orbit the sun, which correspondingly means is that the further planet is, the slower it goes. Now, these nuggets here are the beginnings of the idea of forces, actions at distances. We're starting to get up to this idea that there is a force between the sun and the planets, and that force depends as the radius, the distance away. So as you get further and further away, that force is going down. Kepler's laws are the beginning of these ideas. So to summarize them, the first law says the planets orbit in ellipses and the sun lives at the focus, one of the focuses of the ellipse. Ellipses are described by their semi-major and semi-minor axes. The second law is the law of equal areas. Given equal amount of times, the shaded regions are all going to be the same, regardless of which planet's orbiting. And this just means that as a planet is close to the sun, it must move faster. When it's far away, it has to slow down. And finally, the squared period is proportional to the cubed radius.